Hi, everyone. Welcome to the Banach Spaces webinar. So we meet this in unusual day and time for our seminar to remember the greatest Jean Bourgain. As you know, he passed away 2 years ago, exactly 2 years ago, 1 week from now on December 22nd. And Keith Ball, our speaker here from University of Warwick, he's written one of the tribute articles in the special issue of AMS Bulletin, which is coming up. The talks are already, they are already available online. And he kindly agreed to speak to us on the occasion. So I'd like to thank Keith for this. And so we'll do the usual 50 minutes talk and then we'll open for questions and comments later. I see many of Jean's old friends here. If they like to, make a comment or share a memory, you are more than welcome to do so. So let's get started. Keith, please.
Right, so I share the screen, and there it is, yeah. Is that now visible to everyone?
It is, yes.
Right, so as Benjamin said, I was asked to write an article in memory of Jean, which is going to appear officially next year, although it is available online. And so he asked me to give a talk based on the article. The talk is only very loosely based on the article, but I will explain the main argument in this particular topic that is included in the article. The article actually discusses 3 different areas that Jean worked in, but I chose this particular one. Now, all the material is about 35 years old, so there's nothing new, but it's the end of the year, it's close to Christmas. I thought what I'd do is present some very nice arguments that many people won't have seen because you're all too young. And even if some of the material has been superseded, I don't think it really matters. I think they're very enjoyable arguments. So that's really my aim. Now, the title is Restricted Invertibility here. And I'll explain what that means as I go along. So here we go. The starting point, at least chronologically, is the Kadison-Singer problem, which dates from 1959. Kadison-Singer asked a question about uniqueness of extensions of certain linear functionals, which are called pure states, on C-star algebras. So they were working in C-star algebras, and they asked this question, which looked like a rather technical question within their field. And I think at the time they asked it, they suspected that the answer was actually negative, but they asked the question nevertheless. And about 20 years later, Anderson found a reformulation of the problem solely in terms of matrices acting on finite dimensional Euclidean spaces, which is a much more natural question for people who work in geometric functional analysis to think about. Indeed, I think within that field, it's an extremely natural question. And so I'm going to move straight to this reformulation, explain what that is. So the question in this form asks the following: is it true that whatever number m you pick, there is some integer n, so that if you give me an n by n matrix with zeros on the diagonal, so here it is, and you tell me that it's bounded in norm, so the operator norm as a map from L2 to L2 or L2n to L2n by m, then you can partition the coordinates so that when you look at these principal submatrices attached to the pieces of the partition, so here these lines are supposed to be breaking the coordinates up. You look at these subsets, you look at the principal submatrices, then each of those has a much better bound in operator norm from L2 to L2, from L2 of its dimension to L2 of its dimension, let's say 1. So obviously everything's scale invariant, so it doesn't really matter whether you have m and 1. The point is simply that there's a number r which allows you to get this much improvement in the norm by cutting into r pieces. That's what matters. Now, this hypothesis that zeros on the diagonal is clearly necessary, because otherwise we could just take m times the identity that obviously has norm at most m, and then of course however much you partition it, every piece will still have norm m, so you can't possibly get any reduction. So you have to insist the diagonal is 0 to have a hope of partitioning so as to decrease the norm. So that's what that condition is doing there. Of course, again, it doesn't have to be 0, it could be anything significantly smaller than m, that's what matters. All right, now somewhat after that, not long after that, Tzafriri asked a question about vectors in normed spaces, and he asked it completely independently. So at the time he asked this question, he wasn't aware of, at least of this formulation of Kadison-Singer, so he wasn't aware that he was asking something related to Kadison-Singer. But he asked this question, and he was rather inspired, actually, to ask this question. And he said, and at least in the L2, in the case of Hilbert space, the question reads as follows. He asked a more general question originally, but in the case of Hilbert space, it's the following. So again, somebody gives you a number m, you want to find a number r with the property that if you have unit vectors in Hilbert space, which satisfy an upper estimate on the norm of these combinations, an upper 2 estimate for the norm of linear combinations, then you can partition this family of vectors into subsets, so that in each subset, the set is nicely linearly independent. So it's more than linearly independent. You actually have a lower L2 estimate. So in other words, this set of vectors behaves a little bit like an orthonormal basis in that the norm of this combination is bounded above by m times what it should be for an orthonormal basis, and below by, let's say, a half what it should be for an orthonormal basis. Okay. Now, it's clear that there are some similarities between these two questions, although it's not perhaps completely obvious just how similar they are. I'll be explaining that a little bit later. But before that, I want to somehow connect Tzafriri's question with some things that existed quite a long time before. There's a lovely theorem of Horn, which you might not all know, and if you don't, it's certainly worth looking up and finding a proof of. And Horn's theorem says the following: suppose you've got vectors in a vector space. So I'm no longer talking about a normed space. It's purely an algebraic question. So I have a finite number of vectors in a vector space. And suppose that for each collection of them, they span a space of dimension at least 1 over r times however many you've got in the collection. So if you take any 10 of them, they span a space of dimension at least 10 over r. Think of r as being 2, for example. So every 10 of them span a space of dimension at least 5. Every 11 span a space of dimension at least 6, because at least 5.5 means at least 6, and so on. Then the conclusion is that you can partition this set of vectors into linearly independent subsets, and the number of them is exactly right. It's exactly r. Of course, when I say exactly right, I mean in the other direction, it's obvious. If you can partition them into r linearly independent sets, then clearly, whenever you pick a bunch of them, there must be at least that number over r that fall into one of these linearly independent sets, and therefore they must certainly span a space of at least that dimension. So this theorem is a little bit like Hall's marriage theorem, in that the conclusion is obviously enough to imply the hypothesis, and the subtlety is that the hypothesis also implies the conclusion. It's an if and only if statement rather than just an obvious one-directional statement. So this is a rather beautiful kind of algebraic version of Hall's theorem, and indeed there are ways of relating it to Hall's theorem via matroids and so on. And it's really a gorgeous theorem. And in fact, not only is it similar in style to what Tzafriri asked, but actually there's a connection between them. So this condition that appears in Tzafriri's question does actually guarantee the hypothesis of Horn's theorem with r equals m squared. Okay, so why is that? Well, suppose I pick the Gram matrix arising from these unit vectors. Well, its trace is n, because these are unit vectors, and it's an n by n matrix, so it has ones on the diagonal. And if you had a matrix like that with rank only k, then it must have an eigenvalue of size at least n over k, because when you diagonalize, you've got k non-zero diagonal entries, only k of them, and so one of them must be at least n over k if the trace is n. So so conversely, if you know that the Gram matrix has norm at most m squared, you know that n over k is related to m squared in whichever obvious way it is, in such a way that k must be at least n over m squared. So n over k is at most m squared, and so k must be at least n over m squared. And of course, this works not just for the full set of vectors, the full n vectors. It works for every subset of them as well. You can apply exactly the same argument to every subset and conclude that every subset of them has a subcollection of size at least whatever it is divided by m squared, which are linear independent. They span a space of the right dimension. And therefore, you can apply Horn's theorem, and you can conclude that you can partition the vectors into linear independent sets. So in other words, in Tzafriri's problem, if instead of saying I want an analytic lower bound like this, if I just say I want an algebraic statement that this thing is non-zero, then the theorem is true and it follows from Horn's theorem. Okay, so this is an analytic version of Horn's theorem. We've souped up the hypothesis to an analytic hypothesis, and we want to soup up the conclusion to an analytic conclusion. That's how it works. Okay, now there was another existing theorem at the time that Tzafriri posed the question due to Levasse, which is at least in the same spirit as this Kadison-Singer problem. Actually, towards the end of the talk, I'll explain that what I've said here is not really quite right, but you'll see that in spirit it's somewhat related. And Levasse's theorem says the following: suppose you have again an n by n matrix. This time it's symmetric, which has 0 on the diagonal. And now I'm going to assume that the entries are non-negative, and that the sum of the entries in each row is bounded. So this time the bound is not on the operating norm on L2. It's actually an operating norm on L1, if you want to think of it that way. But from the point of view of this statement, it's simpler just to state it this way: that the sum of the entries in each row is at most m. Then again, whatever integer r you pick, you can partition the indices into sets, so that when you look at these principal submatrices, the rows now have sum at most m over r. So the full thing, the full rows had sum m, and now we've partitioned so that we've managed to reduce the sums by a factor of r. Okay, so you can see that it has the same sort of spirit as the Kadison-Singer problem. You have the zeros on the diagonal, and you're trying to chop down into pieces which somehow behave better. You've got some control over how the whole thing behaves, and you want better behavior for the pieces. That's the same spirit. The problem is in the same spirit. All right. Well, I thought I'd give you a proof of Levasse because it's rather cute. But before I do, let me just remark that the bound is sharp. So if I pick r equals 4, so I'm going to cut into 4 pieces. And just to make the picture easy, let me also assume that m is 4. Of course, it's scale invariant, so it doesn't matter what m is. It's just but I have to choose something in order to draw a matrix. So let me actually take it to be 4. So here is a matrix in which the row sums are at most 4. In fact, they're all equal to 4. And whenever you chop this into 4 pieces, because you have 5 indices, you're going to get a piece with at least 2 indices in it. And whenever you pick a piece with 2 indices in it, the row sum is going to be 1. So you can't improve this m over r, which is 1, because in this example, you will get exactly 1 in the row sum. So the bound is exactly sharp. You can't do better. And the counterexample is the obvious thing, in which these numbers are uniformly distributed over the whole matrix, except, of course, at the diagonal. And you can find examples for every single r. You just make a matrix of size r plus 1 and put 1s everywhere and so on. This was just an example. Right, so I said I would give a proof of this. The proof is really gorgeous. What we do is rather magical. We just choose among all the partitions, the possible partitions into r pieces. We choose the partition which minimizes the sum of all the entries in the pieces. So all the entries with asterisks that I've drawn here, if it were 3 pieces of r is 3. I just minimize the sum of all the entries in the pieces. And of course, the ones on the diagonal don't contribute, but the other ones do. And I ignore the entries in these bits that aren't in the pieces that I'm after. And it turns out that this partition just works automatically. So let's see why. Well, suppose you had a row sum in one of the pieces, and the row sum was p. So suppose here the sum of these 2 things was p. So this is a row sum for one of the pieces. And suppose that sum was p, and suppose it's too big. Okay, we're trying to get down to m over r. Suppose it was too big. Suppose we hadn't achieved what we're aiming to. What I'm going to do is I'm going to take this index. So in this matrix, it's index 5, and I'm going to put it into one of the other pieces. So I'm going to transfer it from this piece where it's bad to another piece. And of course, I choose which piece to transfer it to. I switch the index to the best piece that I can. In other words, what I do is I try and switch it so that the sum that I get from here or from here, whichever piece I switch it to, is as small as possible. Now, what happens to the sum of all the entries in these pieces when I do this switching? Well, of course, the sum decreases by 2p because I've got the row sum p and the corresponding column sum there, p, and I lose those because my index is going into a different piece. So I lose 2p from these pieces here. But it increases because if I put it into this group, I now get the row sum here and the corresponding column sum there. If I put it into this piece, I get the row sum here and the corresponding column sum up there. And of course, the amount it increases depends on, well, you have the entire collection of things here, whose total is at most m minus p. And you're picking the best, you're going to choose the best one. So you're going to choose the one as small as possible. And you've got r minus one of them to choose from. So what you're going to get is at most m minus p over r minus 1. So as long as you choose the best one. And then, of course, you have this factor of 2 because you've got the stuff in the row as well as in the column. Okay? So as long as you're careful about which piece you throw this index into, the sum decreases by 2p and it increases by at most, might be less than this, but of course, in the extreme case, when we've got this matrix, it'll be exactly this amount again. All right, so that's what happens when you try and transfer this index. And I've written that down again here and then calculated the net change, and you calculate it. You can see that the net change is 0. I've just done the calculation here. As long as p is bigger than m over r, which was what it was supposed to be, this is negative. And so that contradicts the fact that we chose the partition with the smallest sum. So automatically choosing the partition which minimizes the sum automatically makes all these row sums less than what they're supposed to be. It's an extraordinarily magical argument. Okay, now I'm going to move towards what Bourgain and Tzafriri actually did. And so in each case, both the Kadison-Singer problem and the question raised by Tzafriri, a natural question is, which is obviously weaker, is whether you can select a fixed proportion of the vectors which satisfy the bound. So instead of partitioning into R subsets which satisfy this bound, can you at least select a proportion, which of course you could certainly do if you could partition. If you partition into R things, then obviously at least one of those would have size n over r. So this is a weaker statement. And it was on this question that Bourgain and Tzafriri published a series of papers. And in the first one, they proved 2 selection theorems. And these are the 2 theorems. Well, they proved a number, but they proved these 2, among other things. And the first says the following. So this is in the direction of Tzafriri's problem. There's a constant so that if you pick unit vectors in Hilbert space, which satisfy this upper estimate, you can find a subset of at least this proportion of n. So m is a constant given by the vectors, and c is this absolute constant, which is in the statement of the theorem. So you've got a proportion of the vectors for which you get indeed this lower bound of c or whatever, c times the thing it's supposed to be. So that was one of the things they proved. So it's a proportional version of Tzafriri's question. And then they also proved proportional Kadison-Singer. So the statement again is exactly as you'd expect. For each m, there's some constant, so that if you have an m by a matrix with 0 on the diagonal, nicely bounded in operator norm, you can find a subset, which is a proportion of the total number of indices, on which you've got a nice bound for the operator norm. Okay, so each of these is analogous to the problems that I stated before, except that we're selecting a proportion as opposed to partitioning, which is obviously a stronger thing to do. Everyone clear about what's going on? Anyone not happy? Okay, good. Right. Now, it turns out that each of these theorems implies the other. And in a corresponding way, when you're talking about partitioning rather than just selection, Tzafriri's conjecture also implies Kadison-Singer and vice versa. This is discussed in considerable detail in a paper of Casaza and Tremaine, Pete Casaza and Janet Tremaine. But I'm going to give a slightly different argument here. And I'll sort of approach it a little bit slowly. So to start with, I'm going to show that if you've got, if you've got theorem 6, if you've got this ability to select a proportion on which you have a lower estimate, then then you can actually improve the upper estimate. So, so you're given a set with an upper estimate, and suppose you know this theorem, then what I claim is you can actually use this theorem to improve the upper estimate for this or any set of vectors. It doesn't really matter. Any set of vectors satisfying such an upper estimate, you can improve the upper estimate by applying this theorem. Okay, that's the first thing I'm going to show. Okay, so suppose we've got such a set of vectors satisfying this upper 2 estimate. Well, what does it mean? It means that when you look at this Gram matrix for these vectors, it has ones on the diagonal, that they're unit vectors, and the norm is at most m squared. Okay, so when I square both sides, I get m squared, and that's another way of stating that the norm of the Gram matrix is at most m squared. But now I want to think of this norm in terms of eigenvalues. This is a nice symmetric positive definite, semi-definite matrix. And so what I'm saying here is that the eigenvalues are at most m squared. It has ones on the diagonal, eigenvalues are non-negative because it's a Gram matrix, and at most m squared. And the previous theorem, Theorem 6, tells me that I can lift these eigenvalues away from 0. Okay, so this restricted invertibility says that by selecting a proportion of the vectors, I can lift the eigenvalues away from 0. These vectors might not be linearly independent. This matrix is positive semi-definite, but there's no guarantee it's positive definite, let alone that the eigenvalues are a significant distance away from 0. But what this theorem says is that I can lift them up to at least c squared. Okay. And what I want to do is decrease the big eigenvalues, right? I want to improve the upper estimate. So I know that by selecting a proportion, I can lift the small eigenvalues. I want to know that by selecting a proportion, not necessarily the same proportion, I can decrease the big eigenvalues. Okay. So why is that? Well, it's sort of obvious once you say that that's what you're going to do. So here is this Gram matrix. If I divide it by m squared, then its biggest eigenvalue is 1. And that means when I look at the negative of that matrix and subtract it and add back an identity, or I subtract this matrix from the identity, I end up with something positive semi-definite. Okay, if I've only got the maximum eigenvalue is m squared, if I divide it by m squared, the maximum eigenvalue goes to 1, and then when I subtract from the identity, I've got something positive. Now I've done it slightly differently here. I've removed the identity, and then what that does is guarantee that the new matrix here actually has 1s on the diagonal again. So it is a Gram matrix in the same sense I'm talking about. It's the matrix of unit vectors, and it's positive semi-definite. So now, of course, what happens is we can pass to a subset in which I lift the eigenvalues of this away from 0, let's say up to a half, and that means that I've actually controlled the big eigenvalues of h, because h appears here with a negative sign. So once I've got this inequality here, I know that the biggest eigenvalues of this h sigma are at most 1 plus m squared over 2. You can just rearrange this and get that estimate. But the right picture to have is that here you see it's the big eigenvalues of h which correspond to the small eigenvalues of this thing. So if I lift the small eigenvalues of this thing, I decrease the big eigenvalues of h. That's the right way to think about it. Okay, so if you're given a collection of vectors satisfying this condition, you can actually, by extracting a subset of a proportion, you can decrease this norm, which is more in the spirit of what we want to do with Kadison-Singer. Okay, what we want to do is decrease the norm rather than bound the thing away from 0. Now, we're not quite out of the woods yet, because the matrix A that I've got here is not necessarily symmetric, and it's certainly not positive definite, semi-definite if it's got 0s in the diagonal. So it isn't a Gram matrix. So I can't quite apply this upper estimate improvement directly. However, we can employ a trick. And the trick is this. So we're given a matrix A, 0s on the diagonal, control of the norm, the operator norm. And now we just form a new matrix in which we square the entries of A. So we just make the entries non-negative by squaring them. And now we apply Levasse to this. So this is just a matrix with non-negative entries. And we know that the row and column sums of this matrix are not too big, because the matrix is actually bounded on L2, which is certainly stronger than saying that its rows and columns are small vectors in vectors no bigger than m in L2. So we know that the rows and columns of this matrix we get by squaring have sums at most m squared. And sorry, most m actually in the case of this. No, excuse me, most m squared. Yeah, I'm taking the square. Yeah, the most m squared. And so we can apply Levasse, partition into pieces, so that when we look at the restrictions, the column sums of these pieces are at most 1. So I've cut down here so that we now have columns which are at most 1. And so what that means is we can now look at these columns and just think of those columns as vectors in L2. So we look at those columns as being these UIs. And they're now unit vectors because I've cut down so that the column sums of the squares are at most 1. So these are now unit vectors. And the statement that the matrix has norm at most m, operator norm at most m, tells us that we have exactly this condition. We have this upper 2 estimate. When we take a linear combination of these columns, we get at most m times the norm of the thing, the coefficients that we're taking the combination with. So we can now apply restricted invertibility in the sense that I talked about it here in Theorem 6 to extract a further subset on which these columns actually behave a little bit like an orthonormal basis. In other words, you get a nice bound. And of course, this is actually stronger than I need because actually what I want to do is then say, well, I'll now chop off the bottom bit and get something even better for this piece here. So the point is that I can actually, after pre-processing with this Levasse theorem, I can now use restricted invertibility to show that whenever I take a linear combination of these columns, the norm is not very big, even when the columns go all the way down to the bottom. And so that's certainly true if I cut the columns off to make a square matrix here, as is requested in Kadison-Singer. So it's a kind of a trick where we pre-process with Levasse before we apply restricted invertibility. Anyone not happy with that? Okay, so now let me come to the, as it were, the meat of the talk and the actual tribute to Jean, if you want to put it that way. So I'm going to give the proof by Bourgain and Tzafriri of this restricted invertibility. So the theorem I'm going to prove is this Theorem 6, and the proof is absolutely stunning, and I make absolutely no apologies for having chosen this particular topic precisely because the proof is so gorgeous. And when I first read it, I mean, when I was quite young, I was completely bowled over. Really, I thought, wow, this is marvelous. So I want to try and convey to you some of the sense of excitement. If you've never seen this proof, if you have, of course, you'll know it. But if you've never seen this proof before, I want to try and convey to you some of this sense of excitement that it created at the time. Okay, so how does the proof go? Well, the proof has 3 steps. And what is bizarre is that the first step, at least, possibly even the second, but certainly the first step, involves proving something so shockingly weak that you can't imagine how it could possibly be useful. And yet it turns out that it is. So the first step is to select a proportion of the vectors which don't satisfy a lower 2 estimate, so not with the L2 norm here, but just with the infinity norm, which is in general much smaller than the L2 norm. So this looks like an extraordinarily weak thing to do, but anyway, that's what we will do. That's what they did. Then the second step is a rather magical argument. So the first step is random. The second step is not random. It's a sort of deterministic selection in which they move from a lower infinity estimate to a lower L1 estimate. So this is now an L1 norm here of the coefficient sequence, but with a 1 over root k. K is roughly the number of vectors that you've got. So everything's a proportion of everything else. So think of this root k as the number of vectors you've got. So they first prove a low infinity estimate, then a lower 1 estimate, and then finally, in the third step, they use another selection, a sort of semi-random selection, in which they get the L2 estimate. So there are these 3 steps, completely different in character, And the middle one is completely magical. So this is in fact, the third one is magical as well, but in a way it's less magical given the knowledge that was available at the time. But the second one is rather marvelous. Okay, so the first one, as I said, was random, and actually once you reinterpret it properly, it's relatively easy. So equivalent to this lower bound is saying that for each of the UIs in the set that you're trying to construct, the proportion that you're trying to find, each one is at least distance a half from the span of the others in that proportion that you're trying to find. So that's just another way of stating the L infinity estimate. Okay, so this is a way of stating it which looks a bit more geometric, a bit more like a Hilbert space sort of statement. And now, once you state it this way, it's easy to see that a random selection will do it. You choose the indices of this sigma 1 independently at random with a given probability, roughly this sort of probability. You compute the expected square of the length of the projection of each of the unit vectors onto the randomly chosen ones that you've got, and you prove quite easily that the expected square of this length is small, so at least half the random collection will have the property you require, and that means that collection will work. Okay, so you take the half of those that you've chosen which have this property and call that sigma 1. So that's a very simple random construction. If I'd asked you as an exercise to prove this and maybe given you this hint about random selection, you would have had no difficulty doing it. So the genius here, of course, was to believe that something so weak could be of any use. So once you've written it down, once you decide to prove it, it's very easy. The second step is not so easy. It's as I say, it's rather magical, and it depends on the Sauer-Scheller lemma, which I'll restate here. So suppose you've got a collection of choices of sign. Now, Sauer-Scheller is often stated for subsets, but I want it for signs, so it's completely equivalent. I'm just looking at the set of ones rather. So if I were talking about subset, I'd be talking about the subset consisting of the indices for which I get a 1 here rather than a -1. But I want to look at this as a collection of choices of sign. And suppose I know that I have quite a few of them. So more than this sum of binomial coefficients. Then the lemma says that you can find a subset of the indices with size at least r, so r being this number here, which counts which binomial coefficients you're looking at. And this subset has the property that whatever choice of sign you put on this, so of all the 2 to the size of Tor choices of sign available on this set of indices, there's an element of the original family whose restriction to Tor is delta. So in other words, whatever choice of signs you put on those indices, you can extend it to a choice of sign which falls into this family whose size you specified in advance. You bounded below in advance. Okay, so if you give me enough signs, I can use those signs, as it were, to give me all possible choices of sign on some reasonably large set of indices. All right. So many of you, I'm sure, are familiar with Sauer-Scheller, but if you're not, I hope it's clear what it says. Right, now, we've stated the lower infinity bound several ways, and I'm going to state it in a third way, yet another way of doing it, and that is to say that the bi-orthogonal vectors to these vectors each have norm at most 2. So the fact that these vectors satisfy a lower infinity estimate in L2 is equivalent to saying that the bi-orthogonal vectors don't have norm too big. Okay. Now, when I then look at the sum of the squares of all these linear combinations of these bi-orthogonal vectors with choices of sign, I know that the sum of the squares by the parallelogram law is equal, or the average of them is equal to the sum of the squares of the norms of the vectors themselves, and that's at most 2 times k. And that means that at least half of them have norm only about that sum. So if I take the square root, it's 2 root k. So at least half of the possible choices of sign, when I form these combinations of these bi-orthogonal vectors, are not too big. They're only about 2 root k, which is what you expect. So they're about k things sigma. These phi's have norm about 1. And so when you take a choice of sign, you expect the norm to be about root k. And what we're saying is that for at least half of them, you don't get something too much bigger than what you would like if these were orthogonal, if these were actually orthonormal vectors. Okay, now what that means by Sauer-Scheller is that there's a set of indices inside this sigma 1 comprising at least half the indices. So I've got so I've got this sum of binomial coefficients, which is half of the 2 to the n to 2 to the k. And that means I can go up to the middle binomial coefficient. That means r is about a half of k, and oh, that n is k, excuse me. Yes, that's causing me a slight problem, but I guess you understood that. So if I've got half of all the possible choices of signs, I can choose a set of indices about half the indices. Okay. So I can find a set sigma 2 comprising at least half the indices, so that every choice of sign on this new set can be extended to a choice of sign on the bigger old set, for which this sum is not too large in norm. Okay, everyone in agreement? Now, how do we employ that? Well, in the sort of standard way. So I've written it down again there. That's exactly what I had in the previous slide. So now if I pick any sequence of coefficients in this smaller set that I've selected, and I look at the L1 norm, remember I want to get a lower L1 estimate, so I want to understand how this L1 norm is related to the norm of the linear combination of the U's. Of course, I use the bi-orthogonal functionals as a functional to test the norm of this combination. So I know that I can write this L1 sum as this vector applied to this one, because the sign lambda I times lambda I is the absolute value, and then phi I ui is 1, and phi I uj is 0 if I and j are different. And now I rewrite this as just some extension. So I've got a choice of signs here on sigma 2, and I know that there is an extension to the whole of sigma 1, some choice of signs of this kind. So I choose the extension with the right estimate. And of course, that has no effect on the dot product here, or the inner product here, because these things are bi-orthogonal. So all the other phi j's that I've introduced here have 0 inner product with all the i's that are appearing, ui's that are appearing here. So I just rewritten this with an extended collection or linear combination of functionals here. And now I apply my norm estimate for the inner product, and this thing then, of course, is at most 2 root k, because that's how I chose which choice of signs, and this is the thing I'm interested in. And so I get a lower bound for that in terms of the L1 norm of the coefficient sequence. So the key is to apply Sauer-Scheller so as to show that you can get an estimate by using what we know about the bi-orthogonal functionals. Okay. Everyone clear about this? As I say, I think this is a rather magical argument. I hope you're all sitting there feeling pretty happy. Good. So now we come to the third step, and Bourgain and Tzafriri in their paper say that they actually originally used a direct exhaustion argument. And I think they do give the argument in the paper, but they mentioned that Nigel Coulton pointed out to them that they could use Grothendieck's inequality instead. In fact, we use what Gilles Pisier calls the little Grothendieck theorem. I noticed earlier that he was here. He sent me a little message. That's very kind of him. Hello. And so here is the little Grothendieck theorem, or one way of stating it. It says there's a constant with the following property. Suppose you have a linear map from L infinity of some dimension to L2. Then you can find a probability measure. So this will be just a sequence of weights adding up to 1, positive weights adding up to 1 on the indices, so that whatever vector you pick in L infinity, the image of that vector, the L2 norm, so this is mapping into L2, so the norm here is the 2 norm. Perhaps I should have written that for clarity, but it's clear from the context. The L2 norm of this image is at most this constant times the norm of t. Obviously, the whole thing is scale invariant. If you scale up t, everything else has to scale up. And then times something that looks like an L2 norm. So in other words, initially you're told that t is a bounded map. So this norm t tells you that it's bounded. So if we were to put the infinity norm over here, that would just be the ordinary definition of the norm of t. But instead we put an L2 norm here with these weights, and we have to choose these weights carefully. But notice that they add up to 1. So this thing here is stronger than the L-infinity norm. It's an L2 norm, but it's better than the L-infinity norm because the weights add up to 1. It's not a sum of coefficients. It's a sum of weighted coefficients. So this is certainly less than the maximum of the thetas. Okay, so this is the Little-Grothendieck theorem, and we employ it in the form that I presented it here. So this is not the only way of writing it, but we employ it in this form. So let's go back to the bi-orthogonal vectors for the set that we last extracted, the proportion that we last extracted, which gave us the L1 estimate. Now, bear in mind, these are not the same bi-orthogonal functionals that we used in the proof. These are now the bi-orthogonal functionals for the new set, right? So of course, bi-orthogonality is a property of an entire sequence. It's not a property. The original phi I is not attached just to one of the UIs. It's attached to the whole family. That's what bi-orthogonality forces. So these are now new bi-orthogonal functionals for the vectors that we selected at the last step. Since those vectors satisfy an L1 estimate, a lower L1 estimate, the bi-orthogonal functionals satisfy an upper infinity estimate with this same constant 2 root k that appears here. Okay. So that means that this map, which takes the standard basis of L infinity of the correct dimension into L2 by mapping each vector to this bi-orthogonal, to this functional psi I, this map is just bounded by 2 root k. It's exactly what this says. So this here again is the 2 norm. I didn't write it, but it's the norm in L2. And so by the Little-Grothendieck theorem, we can find these weights so that this L2 norm satisfies this estimate, which is stronger, this L2 estimate now, which is better. It still has this root k in front, which is not what we want, but we've put in these p's, these weights, which add up to 1. And of course, the key point is going to be that there are k of these, or essentially k of these weights, so quite a few of them are pretty small. So here's the restatement of what I had on the previous slide. At least half of these weights must be at most, let's say 4 over k, because we know that they add up to 1, and there are essentially k of them. So these weights have got to be fairly small. And now, of course, if we restrict attention to those weights, we can pull out this 4 over k. We get a square root of k, which cancels with the square root of k, and we get the upper estimate we want for the bi-orthogonal functionals, which then translates into a lower L2 estimate for the corresponding UIs, the UIs indexed by this particular set sigma. Okay, that's the end of the argument. It has these 3 steps, and as I say, I just find the whole argument absolutely gorgeous. It's one of my favorite arguments that Jean produced, or that anyone's ever produced, at least in my lifetime. And so I couldn't resist including this in the article, and I chose it for this particular talk. Now, I should mention that Kadison-Singer has now been solved, and the process was actually quite gradual. So in 2008, Spielmann and Srivastava found a completely different proof of the selection theorem, Bourgain and Tzafriri selection theorem, the restricted invertibility, using a modification of a quadratic form, step-by-step modification, which a method they also employed Batson earlier for graph problems, graph sparsification. And then 6 years after that, together with Marcus, they managed to prove the solve the Kadison-Singer problem by proving this statement by combining this method with interlacing polynomials. It's a very delicate argument, and in my view, one of the most remarkable achievements in geometric function analysis in the last 40 years. Really, it's an extraordinary piece of work. So Kadison-Singer has been solved in the affirmative. I'm not sure people necessarily really believed the answer was positive. As I say, I think there's even a belief that Kadison and Singer thought the answer was negative. And then, although at some point I think Bourgain and Tzafriri hoped the answer was positive, I think Bourgain may have got to the point where he really wasn't convinced. But anyway, it turns out it is positive and it's been solved. And just to finish with, I was a little bit naughty when I explained the equivalence of the 2 statements. So if I go back to the equivalence of the 2 statements, I said we apply Levasse to this matrix A tilde, but actually the Levasse theorem only works for symmetric matrices, that's not a problem here because we can apply it to the sum of A tilde and its transpose. And because we have a bound on the L2 norm of A, we know that both the row sums and the column sums of A tilde are bounded. And so we can apply Levasse to the sum of A tilde and its transpose, and everything works fine. However, it does rather raise the question, is there a non-symmetric version of Levasse? And indeed there is, and it appears in a paper of Berman, Halpern, Kaftel, and Weiss, which was published in about 88 or 9, I think. But it was proved actually simultaneously by several other people, and this is discussed in the paper of Pete and Janet, Pete Casals and Janet Tremaine that I mentioned before. So this says the following: suppose A is an n by n matrix with 0 diagonal, non-negative entries. It's the same hypothesis, except I'm not assuming it's symmetric any longer. Row sums at most n. Then for each R, we can partition into R subsets so that when you restrict to each subset, the row sums are at most 2m over R. So Levasse says m over R for a symmetric matrix. For a non-symmetric, you have to allow the extra 2, and you really do have to. The extra 2 is the best you can do. And here is an example. That's, again, R is 4, so it's like the previous example. R is 4. In this case, m is 2. So the estimate here is 1, and that is clearly the best you can do. If you partition 5 vectors into 4 pieces, you'll get a pair, and you can see that I've rigged up this checkerboard in such a way that every pair has a 1 either above or below. Okay, so here these two have a 1 above. Here, if you take the first and third vector, they have a 1 in the lower entry, and so on. And so you can't improve on 1, which is 2 times m, which is 2, divided by r, which is 4. So this 2m over r is exactly sharp for this non-symmetric case. It's a rather nice theorem. Any questions?
Yeah, I have a small comment, which is that of the 3 steps that you presented in the proof, actually, I think the third step appeared earlier in a paper by Kashin.
By who?
By Kashin, Boris Kashin.
Oh yes.
Sometimes around 1980, I think.
Right.
And actually, I pointed it out to Lear and Bourgain, well, after they're published, so they were aware, but only after the publication. So they were, of course, they were totally independent.
Sure, of course.
From that, but that was.
Oh, that's useful to know.
This was in some obscure, maybe Armenian journal, something like that. But I was by accident I was familiar with that one.
Well, it's probably from a proceeding at the conference, and the article is in Russian.
Well, could be in Russian, yes, I wouldn't remember. But probably, well, most of them are, well, there are translations that are available if you work hard enough, but of course you have to look for it and know about it, right? So.
Yeah, actually, I always thought that they knew the Grothendieck part before they started, because if you take the capital LP normalization, it makes it easier to say. You have this n by n matrix operating on capital L2 of dimension n, and you do the random choice argument and it doesn't work. And then you say, okay, let's weaken the target norm to be L1. You do the random choice argument, it does work. You actually get paving. They check that you got paving. And then by Grothendieck's inequality, this operator is actually bounded on a weighted L2 space with the weights bounded away from 1 over n. Let's say it's 1 over 2n. And you throw away the peaky part of that, that's the deterministic part, and you get the restricted invertibility theorem. So this is the way I always understood their first proof. I thought that was their first proof.
Well, they said that Nigel Coulton pointed out to them, so I don't know.
So maybe I talked with Tzafriri after that point in order to understand that strategy, and that was an.
You're not thinking of you're not thinking of the upper bound, are you? Because you see, at the time that they first proved it, they didn't realize or they didn't remember that the two things were equivalent.
Oh, right. No, I'm talking about the strategy for getting the upper bound to reduce the norm.
Right. So at the time they proved it, and shortly afterwards, they didn't remember that these were equivalent. So I had mentioned it to Leo some years before they did the work, but I mean, of course, yeah, I mean that's normal. So it was only later that I then mentioned it again, and they put a note at the end of the paper saying that they're equivalent. But no, so when they're talking about this theorem in the paper, they say that the last step was shown them by Nigel.
Oh, okay, I see. Yeah.
Okay, Keith, was that all you wanted to say, or?
Yes. Well, you said 50 minutes. I mean, I could have.
Oh, you can continue a few more minutes if you want to add more. Yeah.
Well, only if people aren't going to get bored. I mean, I don't. I know.
Okay.
All right, if you like. In that case, what I'll do is I will prove this Berman, Halpern, Kaftel, and Weiss theorem, because the proof of that is also gorgeous. What I'm going to do, let me remind you, is I've got an n by n matrix with zeros on the diagonal, non-negative entries. So I want to prove the same thing as Levasse, except I'm not assuming it's symmetric. Okay, and this means that if you apply the Levasse argument, it doesn't work. I mean, it genuinely doesn't work. It's pretty easy to see that it's just not going to work. So what do we do? Well, a little bit of pre-processing. I'm going to assume that m is 1. Of course, by scaling, I can assume that m is 1. Then I'm going to assume that all the row sums are exactly 1. I can always make the entries bigger without damaging the conclusion. So I'll assume that all row sums are exactly 1. That just makes my job harder. And I'm also going to assume that all the entries are strictly positive by approximation. I can always approximate this matrix by something without any zeros off the diagonal. To say all the entries, I mean, except the diagonal ones. Because in a limit, I've only got finitely many different partitions. I just take a limiting partition.
Well, the lecture is done, just questions.
Hello? What?
I think that was an accident. Please continue.
Okay, so what does that mean? It means that A is the matrix of a communicating Markov chain. There's a Markov chain which doesn't split up into separate bits. So any state can communicate with any other state by running the Markov chain. So that means that you have a steady state vector which is strictly positive. Let's call it theta. So it satisfies this condition. So the constant vector is an eigenvector with eigenvalue 1 on the right-hand side. The corresponding eigenvector on the left with eigenvalue 1 is strictly positive. That's because this is a communicating Markov chain. And now, having found this theta, I use the Levasse argument again, but with a different objective function. So now I choose the partition that minimizes this sum, where instead of just adding up all the entries in the pieces, I add them up with this extra weight theta I in front of them. Of course, what's going to happen is that I'm going to take advantage of the fact that this theta is a left eigenvector. So now suppose I have a row sum in a piece whose value is p as before, and suppose it's too big in this new sense. So now too big means bigger than 2 over r, not m over r, because m is 1, but I'm for the non-symmetric case, I'm after 2m over r. So m is 1, but 2 over r is the thing I'm supposed to beat. Okay, so I'm going to switch the index exactly as before, and I'm going to compute how much I gain, how much I lose. Well, the sum decreases by theta I times p. So p is the row sum here, which will be multiplied by theta I, because that's the row in which it appears. And it increases by what? Well, it increases by, at most, what's in here, which as before is 1 minus p, but then weighted with theta I. So that's as before, divided by r minus 1. But then, of course, it can also increase by what happens in this column. So once I switch this thing into a different a different piece, I get the contribution from this column. And now I don't know what this contribution is. So in the symmetric case, it's the same as what I had in the row, but here I don't know what it is. At least I don't know exactly what it is, but I have a formula for it. Well, not quite. I have a formula for it if I crudely throw in this stuff as well. So actually, of course, this is a bit of a waste, but just for the purposes of calculation, I actually throw in this stuff as well. So the worst that can happen is that I pick up all this stuff and somehow this stuff here. And therefore, the total amount that I pick up there is this sum over the ith column of all these entries multiplied by the appropriate thetas, which depend, the thetas are attached to the rows, you see. So, so this is the worst that can happen. It's certainly the worst that can happen because I've thrown in stuff that actually can't happen, but that's okay. This is as bad as it gets. And now, of course, I use the fact that this theta is a left eigenvector, so actually this linear combination is just theta I. And now I'm in a position to understand exactly what this expression is. So there it is on the next page. I'm assuming that P is bigger than 2R. I combine this, I get 2 minus RP. That's less than 0, and therefore I get a contradiction. I chose the partition to minimize this sum, and I've now found a way to switch one of the indices so as to get a lower sum, so as to decrease the sum. And that is the proof of the non-symmetric version of Levasse, this BHKW theorem. And let me just remark that actually this automatically gives us an L1 version of Kadison-Singer. So if you have a matrix with zeros on the diagonal, its norm from L1 to L1 is nicely controlled. Then you can partition into subsets so that the corresponding principal submatrices have an L1 norm operator bound at most 2m over R. That's exactly the same as this theorem here. They're completely exactly equivalent. And now I think I'll call it a day.
All right. Thank you so much for such a beautiful talk. We can open for questions and comments now.
So I've stopped sharing, right? So you're in control, is that correct?
Yes, yes. Yeah, that's better so we can see more people at once. I think Sharik found the reference for it. He put in the chat.
Ah. Oh, hi, Bill, by the way. Sorry, I didn't quite see you before, but I heard you, yeah.
Okay, I suppose there were no other mathematical comments, but feel free to jump in any other comment if you want to make.
I was wondering if there's some interesting open questions in this area currently.
Well, I'm not necessarily the person to ask, since I haven't thought about it for 35 years, but I suspect the answer is probably no, because Spielman and the others, I mean, smashed the Kadison-Singer problem in this beautiful way. But you know, this is a remarkable achievement. It's a gorgeous thing to see.
Well, but in Banach space theory, there certainly is. Bourgain and Tzafriri then applied Kadison-Singer to do restricted invertibility in LP and other spaces. But Kadison-Singer in LP is still quite open.
When you say Kadison-Singer, you mean decreasing the norm,
decreasing the norm
matrix with zeros on the diagonal. Yeah.
Right, with 0 to diagonal decreasing the norm.
So presumably in other LP spaces, these things are not equivalent. Restricted invertibility is not the same as, is not equivalent to decreasing the norm. I can't believe that for a second.
No reason.
Yeah, there's no reason.
Well, no, I'm sorry. Restricted invertibility is certainly always equivalent, right? It's just difference between, well, it implies the invertibility, right?
Well, oh, in one direction, sure, in one direction, yeah, yeah, but the other way around, I mean.
Anything, Gidon may know if there's anything more done. Is there anything more done on restricted invertibility in LP, Gidon?
No, not at all. Of course, as Keith said, it's not in L1, but this is only case. I don't think that I don't know if anything. No.
How is the impact on sister algebras in Kadison-Singer? Like, was there any other, in that theory, in that area, was there any consequence of that?
I have a suspicion they'd all lost interest in it by the time it got solved. I don't
okay.
I don't really know, but
I'm not completely sure. You know, there are some recent works of Bourgain and Levasse. Actually, they are raising open questions, so it also maybe it's a comment for the